So I want to acknowledge my co-author, Johannes Schrader, and of course Alexander Alisov, who did a lot of work a couple of years ago to implement those things we are now working on. It's a great pleasure and privilege to speak here today and to talk a little bit about our work of our group in Braunschweig. My colleagues and I are very much focusing these days on binder testing and mastic testing, as we believe that binder and mastic is the key to improve asphalt, the asphalt properties and the quality. So the outline of my presentation is a little bit of background why we believe that we should not use needle penetration and softening point anymore, and why we believe that we should use new test methods, mostly based on the dynamic shear rheometer. But I'm not so convinced what Markus said before, that we need more complex testing. We need a more complex test apparatus, a test equipment maybe. Dynamic shear rheometers are more complex, no question about that. But we need simple tests, and we need simple parameters to interpret the test, which are based on physical parameters with a physical meaning. And I would like to show you one example how this is the idea we are focusing in Braunschweig. And then I will give you in the end some examples of application of this newly developed binder fast characterization test, as we call it right now in English. In German it is BTSV. I will explain later. So in Europe, bitumen is often characterized through needle penetration and softening point. And these test methods celebrate their birthday. They are 100 years old, and it's time to replace them. And we should do it by new tests. Bitumen type characterization by softening point and needle penetration, as you can see them here for typical German products, they don't work very well. You can maybe very well differentiate with needle penetration, but just the non-modified binders. And as far as the softening point is regarded, there is a big scatter, and we are not able to precisely tell you the characteristics of asphalt materials with such modified binders. We have big problems. So we will not be able to improve asphalt quality by not knowing correctly the binder properties. So there are two conclusions. The traditional methods, they are unable to correctly characterize binders. Many authors have reported about that. And in the US, the pen system, so the needle penetration, the softening point, have been substituted a long time ago by the PG binder system for binder specification. Maybe this could be a better option. We believe that it is not, and we should not overtake this. We should develop our own procedures. So the principle of the softening point method is transferred to a method where we determine the rheological parameters of the bitumen. And for this purpose, rheometers exist. So these is equipment where you can measure rheological properties of any material. So we should rely on the results of rheometers. And there is a couple of different rheometers, and there's a variety of parameters you can change as regards the testing geometry, frequency, load, etc., etc. And we tried to use the dynamic shear rheometer in oscillation mode to simulate the softening point. That was the principal idea by Alexander Alisov, and I remember by heart the day he entered in my office and said, I would like to try to simulate the softening point by using the DSR. and it made really like this, and I immediately told him, that is a very good idea, so please focus on that, and he did so, and this year he finished his PhD thesis on that. So here you can see the simulated softening point, simulated by the DSR. So the output parameter is the complex shear modulus G star, plotted over the ring and ball softening point. So you see quite a big scatter. It does not work. But it is not because the DSR doesn't work. It's because the softening point does not work. And you see this dotted line in a range of 15 kilopascal, and all the plane binders are grouping around this line, which means that the G star, the shear modulus, is approximately 15 kilopascal when testing plane binders at the temperature of the softening point. And for the other bitumen, for the polymer modified bitumen, G star varies significantly. There is a wide scatter. And in the end, you can say the accuracy of the softening point for modified binders is 15 degrees Celsius, which is out of scope. So we cannot use this method. So the softening point does not represent an equivalent rheological property for all our binders. It is not. So that is also why the softening point does not correlate with rheological binder parameters. We have a big problem when using this parameter. So the newly developed binder fast characterization test called BTSV, it's not the Braunschweig Football Club, which we mean here. It stands for Bitumen Typisierungsschnellverfahren. So we tried to translate it in a way, and in the end we came up with binder fast characterization test. There is already a German standard for this method. It's DSR in oscillation mode, and the basic idea is to simulate the softening point for identifying an equivalent rheological binder property at high temperature conditions. We would like to implement this method for binder control, and therefore it has to be simple and fast and has to work for small amounts of bitumen. So the idea was to find something where you can find a very strong parameter within 1 hour. So the idea is maybe in the future to have a DSR at the asphalt mixing plant to check the bitumen delivered, which is nowadays very poorly checked, if it is checked in any way. So test conditions, I skip it now for reasons of sharp time. Here you can see an example of this test method. You find an equi-stiffness temperature, or as we call it right now, the ISU modulus temperature. It's, the idea is a softening point, which is an equivalent rheological parameter for all binders. And as you can see on the graph, it's a or an instationary testing mode, which means that temperature is increased during the test by a constant rate of 1.2 Celsius per minute, starting from 20 to 90 degrees. And then you measure G star, which is decreasing at the same time, of course, because the binder gets softer. So you see the familiarity with the binder softening method, with the softening point method. At the same time, the phase angle is increasing. And now we go to a point where G star gets 15 kilopascal. And that is exactly the point, per definition, where we get our key parameters, which is T, the temperature, PTSV, and the corresponding phase angle, delta PTSV. These are our two parameters. These are the test results. And here you can see a correlation of the temperature TPTSV with needle penetration, it works very well for plain binders and polymer modified binders. So we don't need needle penetration anymore because we get more or less the same output, the same information. And we also do not use the softening point anymore. Here you can see the correlation between softening point and TPTSV, which works very well for plain binders, of course. That is the principal idea of the method. And it doesn't work that well for polymer modified binders because the softening point doesn't work very well. So no surprise. So we propose to use a new system for binder characterization and for differentiation of binders. Here you can see an example of various bitumen called 5070. They are within this box in a diagram built from in a plot where phase angle is plotted over this isomodulus temperature. And we can do the same for all binders, and we get a lot of boxes for the individual bitumen. And we tested now up to approximately 1,000 different binders. So we have a good database to build these boxes. So they are quite strong. And within such a box, all binders are characterized at equal rheological conditions. So it's one family of bitumen. So this works pretty well. So we have our boxes with the two key parameters, and we can now discriminate among the different binders very well. The pity is that the boxes show overlapping. That is because our binder characterization is not very well worked out yet. So if you buy, let's say, a 5070, the rheological properties of this 5070 could be very similar to a 3045 within the overlapping area. With this method, it's the first time where we can clearly distinguish where our bitumen is. So very nice. So what do the parameters tell us? Here are distinguished green boxes and red boxes. So the plain binders, the green boxes, are within a range of almost 80 degrees of the phase angle. So plain binders show a phase angle at 15 kilopascal of 80 degrees, but they are spread from left to the right over the isomodulus temperature, which means that this temperature is a surrogate for the softening point and therefore gives us the binder hardness. So TPTSV corresponds to binder hardness. The second parameter, the phase angle, gives us the degree of the modification. So via the phase angle we can easily distinguish different products by the degree of modification. So maybe in the future we will propose or we will find a new system for binder differentiation, and why not using or proposing a system shown here on this graph. This is proposed by Alexander Alisov in his PhD thesis, and I'm sure it will take decades to implement such a system, but it would be very nice to have such a system. It would be much clearer then. So this is also ongoing research. A second example how to use these parameters is to use these key parameters for evaluating binder aging. As you can see here, there is 5 ... on my, okay, so it's 5070 pen grade binder. So you see the green boxes, and you see how this first green box is developing downwards, and this is because of aging this binder. 1 time in the rolling thin film oven test, up to 8 times. So what we found here is very interesting, and it is ongoing research to test and to check this development for different binders. But if we can confirm this way of development for all binders, this would mean that aging is a linear procedure. And this is ongoing research also together with the Technical University of Vienna, where we want to look at if we find this linear change in properties also on a chemical way. So this is of interest, because if we can find or establish a linear relationship of aging for any binder, we can also predict binder aging. So that would be a very interesting first step in that direction. And last example, where we use the parameters T-BTSV and delta BTSV, is for binder rejuvenation in the high temperature range. I have to tell you something about that in the conclusions. What you can see here, the red dot is aged binder recovered from reclaimed asphalt pavement and modified by adding a rejuvenator. In the first case, a fresh, very soft pen grade binder by 82% and by 100%. And then the second case is by modifying it with a chemical rejuvenator. What we can see here is a very fundamental issue, that if we use fresh binders, we are really moving backwards, we are rejuvenating old binder. It works. And with these two parameters, we can identify the perfect amount of fresh binder. How much do we have to add to rejuvenate the old binder appropriately? Whereas on the other hand, we see what chemical rejuvenators may do. They do not rejuvenate the material in this sense, because we find a horizontal or even a little bit decrease of rheological parameters. So these were my three examples. I come to the conclusions. We think that there is increasing need to substitute the old traditional methods, softening point, ring and ball in the first step, especially when we do routine testing of asphalt binders, when we control quality. The binder fast characterization test using the DSR is a first step in that direction to determine binder properties in the high temperature range. This BTSV, this method, is very simple. Even if you have never worked with DSR, I'm very sure that you are able to do it when we show it to you in 1 hour to do the test. It's very simple. You just need a DSR, but the test itself is really simple. It's rapid, 1 hour, and you have your test results. It's applicable for any binders, even if you don't know the binder. You don't have to check the linear viscoelastic range before testing it. That is a big advantage. You can immediately apply this test method. And the test results are extremely robust. The repeatability is excellent. The TBTSV is binder hardness, and it's a surrogate for the softening ring and ball temperature, especially for the plain binders. And the phase angle gives information on the degree of modification. This BTSV can be applied for binder type characterization, for quantifying aging effects in the future maybe, and for blending of fresh and extracted wrap binders. This I tried to show you in simple examples. But the test is not fully enough to analyze bitumens. We need something in the low temperature range, because what we did right now since the last 100 years is to investigate and to analyze bitumen only in the at room temperature and in the high temperature range. What we really need is something in the low temperature range. And of course you can tell me, why don't you use BBR? Of course we can use BBR, but it would be very nice to have a more simple and a less complex test method. So our idea is to extend DSR measurements also in the low temperature range. And maybe we will be successful within the next 2 years, I hope so, and then I would be very much looking forward to be invited again and to tell you the second part of the story. Thank you very much.